Welcome to a new video in my home automation and Node-Red series, and today I want to talk about a failed project of mine, and that involves this thermal imaging sensor, which is the AMG 3388, and this is an 8x8 thermal imaging sensor, or I think it says infrared imaging sensor. So this is supposed to be a very low resolution thermal camera, and the reason I bought this, by the way, this guy is not cheap. I don't remember the exact price, but I'm going to look it up and add it to the video in post-production. But the reason I bought this because I thought it's going to be so cool if I can have this on the ceiling of my room, and then that would give me like an 8x8 thermal image of the room, and I would be able to tell if there is somebody in the room, because you know, the PIR motion detections are all fine, but the issue with them is that they only detect motion, as in, you know, when somebody is moving around in the room. If I could have this thermal camera looking down, I could pretty much tell, or I should be able to tell, if there is somebody in the room, you know, maybe not moving, but sitting at a desk, or, you know, lying in bed or watching TV, something like that. And the reason I said failed, because it is definitely working. The problem is that if you are a couple of meters away from this sensor, then, you know, standard body temperature, it becomes so weak that it, you know, pretty much blends into the average noise, and it just doesn't have enough sensitivity to, you know, really pick it up and work reliably. And I don't think it's the issue with the device. It just probably just like general physics that I haven't thought about, and it works pretty well in just in a couple of meters, or maybe it would work well in a small room, but like in a living room, it just doesn't work. It's unfortunately not sensitive enough, and also I think it has a probably 60-degree field of view, and I don't have a big living room, but this wouldn't cover my living room either. So that's the reason I put this into the failed project category, even though I, you know, did the initial sketch and the Node-Red integration and everything. So I thought I'd just share it with you. Maybe you can use it for something else. And I think it actually would work fine as long as you are not trying to measure body temperature. Maybe you are trying to measure higher temperatures where the, you know, the distance is not going to be such an issue. I mean, definitely it's going to detect lower temperatures, but if you need an application where you need to tell whether, let's say, something is running, or, you know, like a furnace is on and it's not overheating, then you can still use this to, you know, take decent measurements and, you know, calibrate it, and it's going to work fine. So in the general setup, I'm using a ESP32 development board. I'm using this AMG 8833 that I got from Banggood. And I wanted to integrate a little bit more functionality, so I'm also using this BME 680. And BME 680 is the new type of Bosch environment sensor. So you probably know 280, which measures temperature, humidity, and pressure. This also measures VOC, so this is the volatile organic compound. And I heard that this is also quite good for presence detection, because it would be able to pick up gases that are usually increased in the presence of any, you know, human. So I thought this could be used as well to detect if there is somebody in the room, besides telling it from the thermal image. And the other reason I thought this 8x8 image sensor is going to be a really good use, because let's say if it could cover my entire living room, then I can program it to look at certain areas of the room and detect you know, excess temperature in that part only. So for example, I would be able to locate where the sofa is, so I could tell if somebody is sitting in a sofa, or there is another person in a different type of the room, or if it could see also my fireplace, then maybe it would be able to tell if the, you know, the fire is on just by the emitted heat. So that was the main use of the application. And of course, combined with the BME 680, I would be able to tell probably with certainty if there is any person in the room. The other reason I was using the ESP32, because I was planning to combine it with the BLE scanner, so, you know, detect also mobile phones, which is also a good indicator if there is somebody in the room. Please excuse me for the mess of this setup, but I have quite a few projects running around at the moment. So this is the sensor which is facing me at the moment in my office. So it should be able to detect if I'm sitting in front of the computer. And in the Node-Red part, we can see all the sensor details from this setup. Let me start from the right. So this is the BME 680 sensor. So we have temperature, humidity, the pressure, and the VOC, or this gas concentration, comes in kiloohms. So this is a higher number when the air is pure, and if there are volatile gases, then this gets reduced. Next, you also see some device status. So what is the signal strength for the Wi-Fi and what's the uptime time in minutes? And then, of course, we have the thermal image. And if I move my hand around, you can see that that thermal image changes. I think it's not the right orientation as in the physical orientation and how this picture is, how this image is shown. So if I try to move my hand from here, then I think, yeah, that appears from this way. So this is somehow sort of like, I think it's upside down flipped or something like this. But I'm sitting this way, and you can see the higher thermals on the right side of the screen. I haven't mentioned in the previous part of the video, but actually it is really easy to use this sensor because it uses I2C. So as you can see, I'm using 3 volts and the ground from the ESP, and then I'm using, I think it's D21 and then 22 on this ESP2 board, and then it goes to the AMG image sensor or the thermal sensor, and then it goes to the BME 680, and they are also being powered from the 3.3 volts. So very easy to set up. It doesn't require a lot of wiring, and the fact that I'm using these sensors because they are both using I2C, so it's very easy to use them. And there are plenty of leftover pins on the ESP32 to do something else with this microcontroller. Let's just come back to the image sensor part. In the Arduino sketch, I can specify how quickly I want the thermal image to be updated. And it is happening once every second at the moment, but the sensor is capable for more frequent updates as well. But I thought, you know, just to process data and see how it works, 1 image per second is going to be more than sufficient for me. And actually what you are getting all the data from the sensor in exact temperatures, and this is what you can see on the screen. Of course, it might need to be calibrated, and I don't know what emissivity settings it uses, but this is what you get out of the device, or at least what you get out of the Arduino library. And if I look at the code, we can actually see that. And I'm just piping that through to MQTT, and as you can see, the 64 settings are coming through as simple comma-separated values in an MQTT topic, which is called the thermal/thermal. And I also have another topic which is thermal/BME and thermal/status, where I'm getting the status and the BME readings, and they are all getting all coming through in JSON format. And it's going to take some time because I think the status is once every 10 seconds and the BME is, no, status is once per minute, I think, and the BME is once per 10 seconds or something. But it's all configurable in the sketch. And as you can see, it comes through as a JSON. And I'm just using the Node-Red to display this screen for the 64 readings. So, this is just a simple HTML table where the background changes based on the temperature, and I'm using the simple color palette which goes from blue to red. And here I have the min temp and the maximum temp. These are just the statistical values that I use to scale the color of this image. So it will find the minimum and the maximum temperature in the picture, and if the 2 is less than 10 degrees, then well, the maximum is going to be 10 degrees minus the 10 degrees above the minimum, because otherwise this image gets too much saturated. And if I put my hand really close to it, you can see that the temperature rises and the image is updated. So it works. You can see and as you can see, so at the moment it is registering my hand temperature is like 31 degrees, 32. And as I start moving this away, this is probably like a meter, and it's already dropped by 2 degrees. And if let me just roll back in my chair to about 2 meters. And as you can see, I'm still about like, 3 degrees above ambient. But if I move further away, then it really becomes, very close to the background noise, which I think it makes it unsuitable for that sort of human detection that I had in mind. And I think by itself this flow is interesting enough, but what I wanted to add is I wanted to add these rules where I can specify that I would be looking for events, let's say when the maximum temperature in any of the pixels exceeds 32 degrees. So if I put my hand really close to it, then you say that this rule evaluated to yes, because the warmest pixel is 32.24 degrees. So that would be something like, there is a person in the room because there is like a really high peak temperature. The next one, I also wanted to create a rule where, let's say, only a certain pixel in this grid exceeds a temperature. So the top left corner, if it exceeds 30 degrees, and now I need to move my hand. Actually, I need to move my hand really close to it. No, this way probably. And yeah, now we have detection 3175. So I think this would be the type of the rule where, let's say, you can set this up to detect the gestures. So if it's looking at you, you raise your hand that way, or you raise your hand that way, and it would be able to detect the gestures. And the last one is this, am I at the desk? Is I think it's looking at this 4 pixels or this 4 pixel quadrant, and again it's looking for whether the average temperature exceeds, I think, 27 degrees or something like that. So because I'm sitting sort of offset that way from the image sensor, it's going to see me in that quadrant. So I'm sitting in front of the desk, so it says yes, you are sitting in front of the desk, and that's the average temperature of these specified pixels. And if I start rolling back in my chair, then I'm probably like 2 meters away from my desk now, and it says, well, I'm not at the desk anymore. So it definitely works, and even this simple code works, and you can set this up to do, various things and detect various different scenarios using this image sensor. But yeah, it just wouldn't do the task that I had envisaged it for. And let's look at the Node-Red flow. And I'm sending data through 3 separate MQTT topics. The one is the status topic, where I'm getting status information, which is basically just the RSSI and the uptime. And then I'm also sending the BME 680 sensor data. So there's temperature, humidity, and pressure, and the VOC, or the gas component of the measurement. And I'm getting the thermals. The raw thermal data looks like this. So it's 64 float readings separated by comma in a simple text. And here I'm using this function node to render this into the image that you see here. And I have a color palette up on the top. So these are my colors in the hex values from blue to red. And there are, I think, 255 values. And in the rest of the code, as you can see, I'm just creating an HTML table in text, and doing all sorts of parsing of this input data, converting into the actual float, from this string to float. And I'm using linear interpolation to map the temperature values to the 255 color values. So you see, these colors as from blue to red here on the screen. And actually the HTML source code is, very lazy, because for every single pixel, I'm just specifying the color and also the font size and the font color. So it becomes a very, big HTML code. But yeah, Dashboard is able to deal with that without any problems. And yeah, once I'm done with that, and I'm pushing these values out, and I'm displaying the image, a simple UI template. So that displays this image, and I have the minimum, the calculated minimum and the maximum temperature shown here. These were just for me for debugging purposes. That's the display or the imaging part of the flow. And what else I'm doing with this thermal image, I'm also piping through this rule engine, and this is responsible for evaluating whether these rules that I have specified, these are either true or false. And I'm also providing a value that decides whether this is true or false. So again, this was for me for debugging purposes, so I could see what the code is doing. And the way you specify the rules, you can see them in these inject nodes. And all of these inject nodes, they inject a specific JSON payload where the topic is set rule. And in this JSON payload, it has a few things. It has a name, so this is maxtemp. It has an aggregation method, and at the moment it supports max and average, nothing else. It has a value and it has a weight. And this weight is an 8x8 matrix. And what it does is, in here I say that in the weight you can specify which pixels to look at. So you can have either a 0 or a 1. I mean, technically you can have any values between, but here, because I have 64 ones, I'm saying that I want to check the max temperature in every single pixel in the image. And I'm looking for the max temperature, and if the max temperature is above the value, then this rule is going to evaluate as true, otherwise it's going to evaluate as false. So yeah, fairly simple. The next one was the corner rule, and as I said, the topic has to be set rule all the time, and then the payload is always the same JSON. Of course, it has a different name. It has again an aggregation, which is still max. The value is 30 at the moment, and you can see that the weight, I've only specified the top 3 pixels. So these three pixels that are used in this calculation. So whatever happens in all the other pixels are just basically getting ignored because the value is 0 for all the rest. So this was my corner detection, like my gesture, whether I'm pointing my finger in the top left corner or something like that. And finally, I have a rule for the at the desk, which is a slightly different payload. So the name is at desk, and here the aggregation is average and 25, and then I have the weights, and I said I specified the, I think, top left, top right 4x4 corner. So from the first row I need the last 4 pixels, and again last 4 pixels, last 4 pixels for the first 4 rows, and from the 5th rows onwards everything is 0. So it's going to look at this quadrant of the screen and average all the readings, and if they are above 27 degrees, so at the moment it's 28 point something, then the rule is got evaluated to yes. And everything is done here in the rule engine. I'm not going to go through this code. I have left some comments here so you can go through it, and of course, if you want to really use this, you probably have to create more aggregation rules. And you can see my comments here. This is where I handle when the aggregation is max. This is where I handle when the aggregation is average. And also I have, for the average, I also needed to add this rule, which does the final calculation. But what you get out of these rules is, for every single time the thermal image comes through, it's going to evaluate all the rules that you have specified, and it's going to output the results in the output node. And as you can see, every time you are getting 3 messages, because I have 3 rules that got evaluated: the max temp, the top left corner, and the at the desk. And they would always have a result which is true or false, and you are also getting some values back. So for example, the at desk, it says that 16 cells were used in the calculation. The threshold value is the value that the average value is 29, and the threshold was 27. So this is why it's yes. And the debug array has all my pixels, and I was using this for debugging purposes, so you can see what the code is doing. But as you can see, every time I'm getting the max temp, the left corner, and the desk back as evaluated rules, and I just display the results on the screen at the moment. But you can use this to do, like, if you are at the desk, you turn on the lamp. If you leave the desk so it changes to false, then you turn off the lamp. Something simple like that. And the way you would use this is, you have to inject these nodes, and because they have this topic set rule, this function node knows that this is a new rule, that it needs to be stored, and it gets stored in the context. And every time a thermal image comes through, it basically looks at its context, and it looks at all the rules that have been saved. So if you implement my flow, then nothing is going to happen at the beginning. You have to click on the inject nodes, and that's when the rule is getting saved. And from that point, that rule is going to get evaluated. So let's say in a production environment, you would set these inject nodes. So they inject once Node-Red starts. And from that point, all these nodes are going to evaluate it. And there is no limitation how many rows you can use. I mean, maybe there is a technical limitation how much of this logic Node-Red can run in every single second, but I'm assuming that could be like dozens. So you can use one single sensor to detect, many different scenarios. And that was the main, purpose of this project as well. And let's just have a quick look at the Arduino sketch as well. As I said, I was planning to use this setup for different tasks as well, but what is implemented in the sketch is just the AMG 8833 thermal image sensor and the BME 680. You can see the libraries that I used here. So up in the top, you can specify what is the sampling rate in milliseconds. So it's 1 per second for the image sensor, every 10 seconds for the BME 680, and every half a minute for the status message. The main thing you have to focus on really is this top section here in this sketch where you specify your SSID, your password, and your MQTT server details. And of course, you can check the MQTT topics as well. And the rest of the code is really not something that you really need to know about. I mean, you can look at the details. I've also included an Arduino OTA sketch here, so I can just easily upload the sketch, especially if it's mounted up on the ceiling. But I haven't used it up until now, so you can just leave it in. It's not going to make a huge difference. One thing I had to change is I had to set the buffer size for the MQTT server because the thermal image was longer than, I think, 256 or 128 is the standard, maximum size for the MQTT messages, and I needed more, so I increased it to 512. But besides that, in the setup section, we are setting up the BME sensor. We are also setting up the AMG image sensor, and the rest of the code is, just the standard stuff. So there is an MQTT reconnect node, there is an MQTT callback code, and this is the code to get the BME 680 sensor. By the way, everything gets logged into the serial output as well, so you can look at the messages there as well. That's the part which is generating the status that gets sent out in MQTT format. And reading the AMG sensor, as I said, is really simple. It just gives you an array with the 64 values, and I just concatenate that into the string that I pass it to MQTT. So as you can see, I'm just putting that into a string with comma separation, and then I'm passing it to the MQTT publish. So that's it. And in the loop, I handle the OTA, the MQTT reconnection, and also I have this few stuff which is basically checking which sensor needs to be read, whether it's the BME 680 or the image sensor, or the status needs to be updated. And yeah, that's pretty much it. So this was the video of my failed AMG 8833 project. If you are still interested in this project, I'm going to leave a link for the Arduino sketch in a GitHub repository for the code which is running on here at the moment, and I'm also going to leave the Node-Red link which processes the thermal image. But that's all for now. Thanks for watching, and hopefully see you in the next video.